All right, so if you could only smell what's going on in here, I have coffee brewing because after that last mishap from the last video, I feel like I need some caffeine. All right, so this is just an example. I would kind of like recommend kind of going through, make sure you understand it. And you can do it kind of like on your own. You learn nothing by watching me just do a bunch of math the same way that I would learn nothing if I just watched you go to the gym and like squat a bunch of times. I'm not going to get any stronger. So in terms of the examples, right? So let's kind of look at how this function changes, right? So my if my function was y equals x to the third power, right? So here's my y equals x to the third power. So in essence, we have y plus 5, right? That's kind of the idea, this plus 5. It's affecting the value of y. This is a range change because we're affecting y's. So if I have every y value, I add 5, it's going to move our function up 5 units. All right, so if I want to sketch x cubed plus 5, I'm a fan of technology. So if you want to just like go into Desmos or something and graph the scene, by all means do it. But x cubed, we'll talk about this a little bit more. Actually, I have some things that I'll kind of throw into the like Blackboard, right? This is x cubed. So if I take this entire function and I shift it up 5 units, it's just going to look something like, say, that, right? So this is going to be x cubed plus 5. Where this distance here is 5, this distance here is 5, and so on. All right, so now let's find the difference quotient, right? So I already told you what x plus h to the third power is, but I don't want you having to like derive that thing, especially, in this case. So again, let's just write out our difference quotient, right? So our difference quotient is going to be f of x plus h minus f of x all over h. All right, so we know that our function f of x is x cubed plus 5, right? So I know this part of the function already. Again, be careful with subtracting. So f of x plus h is going to be f of x plus h cubed plus 5. Again, I told you what x plus h to the third power is, right? You don't have to expand that thing out, right? So this is going to equal x cubed plus 3x squared h plus 3xh squared plus h cubed. And don't forget that there's still that 5 hanging out at the end. All right, so now if I can get rid of that thing. So now if I plug things into my difference quotient, I'm going to have f of x plus h, which is this thing right here. And I'm going to take away my f of x, which was x cubed plus 5. And this whole thing is divided by h. Remember, if we're working with a polynomial, right, this whole f of x term should cancel. That's a pretty easy giveaway that you've done something wrong. If you have, say, an x cubed that kind of lives on, or a 5 that lives on. Right, I'm subtracting x cubed and x cubed, so those are going to cancel. I'm subtracting 5 and 5, so those are going to cancel. So the only thing left over is 3x squared h plus 3xh squared plus h cubed all over h. And then once again, I can factor an h out of everything. I get a 3x squared plus a 3xh plus h squared, all divided by h. So these h's cancel, and we're left with our difference quotient of 3x squared plus 3xh plus h squared. So we have a little bit of a more complicated equation for the difference quotient than we did in the previous question. Right, so we can see here that's kind of nice, right? It's just the X and the H, right? Those combinations of those things that kind of worked. But here there's kind of like synergy that we need to keep track of if we were trying to use this for our slope. Not only are we taking our starting point of X, squaring it and multiplying by 3, there's also some product of X times H. Where are we starting times how far away are we moving, right? So it's not kind of clear how this kind of movement of X plus H kind of changes our slope here the same way that it was for the previous question. All right, so if we wanted to just figure out some slopes here. So if I just gave you one point and I knew how far we were moving away from it. So I'm starting at x is 2 and I want to move 3 away from it. So then our difference quotient, aka the slope of the secant line. Well, if I'm starting at x is 2 and I move 3 away from that value, right? So aka I go to 5, I can just plug these values in. I have 3 times 2 squared plus 3 times 2 times h plus h, whatever the value of h is, squared. My value of x was 2. My value of h was 3. So if I calculate this, I'm going to get 3 times 2 squared. So that's going to be 12. plus 18 plus 9. So that's going to be 39 as the slope of my secant line. So another way you could do this is you could say, well, I'm at x is 2 and I move 3 over. So if I'm at the points, let me just make sure that 213 was the actual point because, sometimes we make mistakes. Oh, not for this one. So if f of x is x cubed plus 5, f of 2 is going to be 2 cubed plus 5, which is 13, right? So we have this point 213, which is on our graph. So if h is 3, remember, h, kind of think of it as like a horizontal shift, right? I'm shifting my x over 3 units. So I'm going from 2 to 5. Right, so that's a 3-unit change. So that means f of 5 would equal 5 cubed plus 5. 5 cubed is 125, plus another 5 is 130. So we have the point 5, 130 on our line. You could do the old school way of finding the slope, right? Change in y. If I'm going from 13 to 130, I'm going up 117. I'm going over 3, 117 over 3 gives us 39. You get the same slope doing it that way. So if I want to find the equation of the line in Taylor form, well, if Taylor form is new, just write it out. F of x equals our y coordinates plus our slope, x minus x sub 0. Our y coordinate is 13. We found our slope to be 39. And so we have our variable x. What are we taking away? What's our x coordinate? 2. And so this would be our equation of the line in Taylor's form. 13 plus 39 times the quantity x minus 2.